So in the last video, we were able to determine by Hund's rules that triplet F was the ground state. That meant that triplet P is the only spin allowed excited state. Triplet F was the ground state because it minimized electron repulsion. The two electrons were in orbitals that were in different planes. The triplet P was the excited state because it put electrons, although in different orbitals, because it's a triplet, in orbitals that were shared a plane, and so that increased electron repulsion. All right, so here we are. Now we can get to some good stuff. We have triplet F ground state, triplet P excited state. Spherical ion. No ligands, not octahedral symmetry. At this point, all 5 orbitals, d orbitals, are the same in energy. We're going to define a term here called 15B. It's a unit of energy. B is a unit of energy. B is called a Rockoff parameter. It's a measure of electron repulsion. Why are we putting it in terms of electron repulsion? Because remember, that's what distinguishes the triplet F and the triplet P, is that added electron repulsion from the triplet P being in the same plane, those orbitals being in the same plane. So we're going to call this 15 times B, and B is a Rockoff parameter. There are different values of this B for different ions. And you can look these up, and I'll show you how to do that later on in the course, in this chapter. But for vanadium 3+, B equals 860 wave numbers. So it's a unit of energy. So 15 times 860 wave numbers, that would be the energy gap between the triplet F and the triplet P for spherical free vanadium 3+ ion. Now we also have our spin forbidden states, singlet 1D, singlet G, singlet S. Those states exist. Those are real states. They can be probed using other more advanced types of spectroscopy that we're not going to talk about in this course, but I'm graying them out because we don't really care about them for UV-vis spectroscopy, because those will be spin forbidden. They'll be very low probability events. They will happen, but they'll be swamped out by this triplet F to triplet P transition. And again, how did I figure out singlet D's here below triplet F and singlet G and singlet S? That comes from more complex calculations. All I can do with what we're learning right now is triplet F is the ground state due to Hund's rules that we went over in the last video. Okay. So these are the electronic states when all the d orbitals have the same energy. Yes, that's what we said. Spherical ion, all 3 d orbitals are in the same energy, pentuply degenerate. What happens when we impose an octahedral ligand set? All right, this is where things get interesting. So now we go back to the triplet F. These are 7 pairs of orbitals that make up the 21 microstates. Remember, there's 21 because there's 3 different spin combinations. Spin up, one spin up, one spin down, all spin down. So these are 21 microstates in the 7 pairs of orbitals. How do all these pairs of orbitals transform in octahedral? Well, we know that the XY, the XZ, and the YZ transform as T2G symmetry in octahedral symmetry. And we know that the Z squared and the X squared minus Y squared transform as EG in octahedral symmetry. So here we go. This is where things get pretty interesting, okay? We're at the triplet F. So now we can come up with an energy term for these 3 orbitals, okay? Notice these are all, both orbitals are in the T2Gs. Basically we have, I mean, you could write out the electron configuration here. And for these 3 orbitals, now that we're in octahedral, we're thinking about octahedral, right? You could write that out if you wanted to as a T2G2. Both orbitals are, both electrons are in T2G orbitals, okay? And so the energy of this is going to be 0B. Why 0B? Because we're at the ground state. In terms of electron repulsion, this came from triplet F. So there's not any additional electron repulsion. And we're also at T2G, okay? So remember, right, that in octahedral symmetry, you have your T2Gs and your EGs, right? And we call this energy gap delta O. Well, if you have electrons like this, for example, in T2Gs, T2G2, you also do not have any contribution due to delta O. So basically the energy is zero relative to our baseline. Okay? It's our baseline, the most stable of states. Now, what about these? These have one electron in the T2Gs and one electron in the EGs. So we could write these three sets of orbitals. These would have T2G1, EG1 electron configuration. Again, it's a triplet F that this is coming from, so there's no additional electron-electron repulsion. All these orbitals don't share a plane. But now you have a situation like this, for example, where one of the electrons is in the EG. So that costs you 1 delta O's worth of energy. And what about here? Both electrons are in the EG. So I have an EG2 electron configuration. Again, your triplet F, different planes of these orbitals. They don't share planes, so minimal electron-electron repulsion. But now you've got 2 electrons in the EG. And so that, since EG costs you a delta O penalty for each EG, that's why you have 2 delta O. Lastly, these are term symbols. We went over in a previous video how to figure out term symbols for molecules. And we said that if you're a singlet state, it was easy. It was totally symmetric in a singlet. If you're a doublet, it's very easy. It's a doublet. And there's just a symmetry of wherever that unpaired electron is. These have multiple unpaired electrons. These are triplets, 2 paired electrons. I didn't teach you, and we're not going over in this course, how to get the term symbols. I'm just going to tell you what they're called. Okay. This one, they're all triplets, of course. And they have symmetries triplet T1G, triplet T2G, and triplet A2G. Those are the term symbols of what we call these. Okay? So the triplet A2G is going to be the highest in energy as this 2 delta O term. Triplet T2G is going to be intermediate, and triplet T1G is going to be the ground state. Now, let me clear all this writing that I did and go back to now the triplet P. Triplet P, this is a very key slide here. Triplet P, we have 3 sets of orbitals here. These share planes, right? And because these share planes, they have, we said they're excited state, right? They were excited state. And so these have a 15B, they have that 15B term. Where'd that come from? Remember, that came from this. So anything that starts at triplet P has that extra 15B of energy due to electron-electron repulsion for these triplet P orbitals being in the same plane, okay? So 15B, and then 1 delta O. Why is there 1 delta O? Well, similar to what we said before, what's our electron configuration? Look at all these. They are T2G, 1 in the T2G, 1 in the EG. 1 in the T2G, 1 in the EG. 1 in the T2G, 1 in the EG. Okay? So all these are the same. They have the same electron configuration, T2G1, EG1. Okay? So that's going to look like this. Again, this was delta O. This is T2G. These are EGs. So we got penalized for having that 1 electron in the EG. So that's where that 1 delta O comes from. So the energy of the triplet P's is going to be 15B plus 1 delta O. The term symbol for this, again, we haven't learned how to determine the term symbol for triplets in this class. I can refer you to books if you're really curious. It's not that important. This is also a triplet T1G. And unfortunately, things get complicated. Here we have a triplet T1G that came from the triplet F. Here we have the same thing, same symmetry, triplet T1G that came from the triplet P. But those are distinct states that have different energy. So this is a summary of everything we just did, electron configurations, the energies, how they split in octahedral symmetry. All right, and so let's stop there, and next we're going to be able to make a Walsh-type diagram going from spherical symmetry to octahedral symmetry.